Today, we want to continue on our finding antiderivatives journey. Yesterday, we took a quick detour into using the second fundamental theorem of calculus to construct an antiderivative. So that's always on the table. If we can't find an antiderivative, we can always build one. So this antiderivative business has no holes in it. We're always able to do this. Sometimes we're able to find a nice formula for what the antiderivative should be. And so that's one of the skills that we want to acquire. We started with our most popular, the integral of x to the n dx is 1 over n plus 1, x to the n plus 1 plus c. This only works if n is not -1, so we have to fill that gap in. So this is true as long as n is not -1. We should also note that sometimes instead of writing 1 over n plus 1 separately as a factor in front, some of you are going to prefer to write x to the n plus 1 over n plus 1. So some of you will prefer to write x to the n plus 1 over n plus 1 plus c. I personally prefer having my constants out in front rather than shoving my constants underneath the x. I like the constants to be the coefficients, excuse me. I like my coefficients to sit distinctly in front, even if it's just going to be a 1/3, even if there wasn't something there to start with. But that's just me. It's totally okay if you want to remember this as x to the n plus 1 over n plus 1. It's not strange at all, despite what I might say. So we have to cover the gap when we have n equals -1. And for that, we have the integral of 1 over x dx is the natural log of the absolute value of x plus c. The important thing that we don't want to do, that we want to remember, is that just because stuff is in the denominator doesn't mean that we're just going to put a natural log in front of things. This is specifically for 1 over x. If I have a 1 over x squared, that's not an x to the -1, so I'm not worried about the natural log business. If this is a 1 over x squared, we just read that as x to the -2, and we can do the add 1 to the exponent, divide by the new exponent. Don't just start natural logging stuff when you're integrating when something has a denominator. Some people get a little crazy with the natural logs. They're just like natural log all the things in the denominator. But it's only when the exponent is -1. All right. Here's the good news. Since we know a lot of derivatives already, and we know the relationship between integrals and derivatives, we just kind of like double our knowledge. Everything that we have that's a derivative statement now is an integral statement. So all of our derivatives, all of our base model derivatives that we use to build other things, that we use to build other derivatives with product rule, quotient rule, chain rule, those are all antiderivatives that we know as well. So all our derivatives are now antiderivatives too. All of our known derivatives are now known antiderivatives. So we know that the derivative with respect to x of, say, e to the x is e to the x. That's a statement about derivatives. We can turn this around to a statement about integrals. Since the derivative of e to the x is e to the x, the integral of e to the x dx is e to the x plus c. We have to remember in the antiderivative direction to add the constant of integration. A lot of times, we're not just dealing with an e to the 1 times x. Sometimes there's going to be a coefficient with the x. We know how to deal with that with derivatives. So if I have the derivative, the variation on this is if we have the derivative of e to some constant times x, we know we have to use the chain rule. In this case, the derivative of the inside is just a constant. So the derivative of e to a constant times x is e to the constant times x. And then we use the chain rule and multiply by k. So that k comes in from the chain rule. The derivative of the inside is just the constant k. So that k comes from the chain rule, but it's just a constant. We want to be able to integrate. We need to be able to do the inverse of this. We need to be able to integrate an e to the kx. So when we take the derivative of e to a constant times x, we got that constant times e to the kx. So if we multiply by k when we're taking a derivative, what do you think we do when we're doing an antiderivative? We'll just divide. It's just as you would suspect. So the integral, the more useful version of this integral of e to the x is the integral of e to the k times x dx. So the integral of e to the kx is e to the kx, and then we divide by k. And then we put plus c. Since the derivative of the inside was just a constant, I can just divide by that constant. Note that if we take the derivative of 1 over k e to the kx, the 1 over k follows along as a constant multiple. The derivative of e to the kx is k times e to the kx. The k's cancel out and leave us with just an e to the kx. So everything checks out. So if we had the derivative of 1 over k e to the kx, that's going to be 1 over k times k e to the kx. And so that'll just be e to the kx. So seems to check out. So this is a little bit more useful form of the integral of e to the x, when we have an e to the constant times x. You don't have to memorize this, but you do have to remember it starting now and going on till forever. You can't just remember this one for this class. You have to remember this one forever. One of the quizzes that you have in this class doesn't take place for another 3 years. In 3 years, I find out where you're working, and I like show up with a quiz. Like, well, what's the integral of e to the 5x? And then you've got to be like, well, Professor Leach, get the heck out of my place of business. I will, as soon as you tell me the integral of e to the 5x. And if you don't know, I go back and change your grade. At this point, it doesn't really matter because you graduated and stuff like that. But I'm kidding, I don't do that. depending on the security level of where you work. But if you're like a checker at a grocery store, at one point you'll be like checking groceries, and all of a sudden a piece of paper will come down the belt. You'll pick this up, and what the heck is this? And it'll say top 2 quiz, integral of e to the 5x. You'll be like, oh, what the hell? And then you'll look up and I'll be like, standing there, Michael, you got 5 minutes. This is for a grade, so I'm just kidding. Some of you are like, oh, ha ha. We're millennials and Gen Z. We won't have jobs in 3 years. Boomers took care of that. All right, so what we want to do is take all of our derivative knowledge and turn it into antiderivative knowledge. And all we have to do is turn things around. So let's take some things that we know. The derivative. I'm just going to switch over to this constant times x version. The derivative of sine of k times x. The derivative of sine is, the derivative of sine is cosine. So the derivative of sine of kx is k times the cosine of kx. This gives us an integral statement as well. The integral of cosine of kx is going to be 1 over k times the sine of kx. Once again, that k is showing up just from the chain rule. Since it's a constant, I can just divide both sides by the constant. Differentiation and integration respect constant factors. They just ignore constant factors. Carry them along. We also have the derivative of cosine is negative sine. So when we turn this around, the integral of sine will be negative cosine. All of our derivatives are now antiderivatives. We know all these derivatives. We now know all these antiderivatives. We know that the derivative of tangent is secant squared. So the integral of secant squared is tangent. All these derivatives that we have running around are now antiderivatives that we have running around. All we have to do is remember them. You don't have to memorize them. You just have to remember them all. We know that the derivative of secant is secant tangent. So now we know that the integral of secant tangent is secant. All these derivatives that we know become integrals. Early on in the process, when we're learning integrals, we don't technically know the technique of substitution, which is an anti-chain rule. So we're just using the simplest form of integration by substitution, which is the anti-chain rule. It's just constants, so we don't have to worry about too much. Mostly because derivative of constant times a function is that constant times the derivative of a function. So the integral of a constant times a function is that constant times the integral of the function. Any questions? These are just things that you know now. As an analogy, at one point in your mathematical career, you learned that 7 times 8 is equal to 56. And then you learned that multiplication and division are related. So knowing that 7 times 8 is 56 gives you two things for free. 56 divided by 7 is 8, and 56 divided by 8 is 7. It's like that one piece of information contains 3 pieces of information. Buy one, get 3, that's a great deal. Here, we had this information already. We're just expanding what we know about it. We know that the derivative of e to the kx is k e to the kx. So we now know that the integral of e to the kx is 1 over k e to the kx. Instead of just multiplying by the constant, we're dividing by the constant, which makes sense because we're doing the antiderivative. We're doing the inverse of the derivative. There's a couple more that you need to know. I don't think I'm going to fit them. Should I try? Probably not, but I'm going to anyway. Definitely won't fit. And it'll bug me if they're not together. So two more derivatives that we know are the derivative of arctangent and the derivative of arcsine. The derivative of arctangent is 1 over 1 plus x squared. The derivative of arcsine is 1 over the square roots of 1 minus x squared. So now these two derivative statements are integral statements that we know. The integral of 1 over 1 plus x squared is arctangent. And the integral of 1 over the square roots of 1 minus x squared is arcsine. So arcsine and arctangent are the inverse sine and the inverse tangent. So you might also see this as sine to the -1, which is not how you will read that. That's just how you spell it. You would read it as sine inverse. So these are just other words for sine inverse. We write it as sine to the -1x, but we don't mean the -1 as an exponent. We use the -1 exponent to indicate an inverse. This is a bad habit that we developed a long time ago, and we're just kind of stuck with it now. When we first started writing this as sine inverse, we were like, oh, dude, maybe we should come up with something else because that looks like a -1 exponent. And then a bunch of other people are like, oh, a bunch of other mathematicians are like, oh, no, it'll be fine. It'll be clear from context which one we mean. Then we started teaching people trigonometry and like, oh man, it is not clear from context. Some students are reading that as a -1 exponent. But mathematicians are going to mathematician, and they're like, oh, we'll just run with it anyway. And so sometimes you see arcsine as an alternative to writing a -1 exponent when you mean an inverse function. That's just one of those weird things that happens in math. So arctangent is just inverse tangent. And we could just similarly write that as tangent to the -1. We can spell it, we can spell it tangent to the -1. But when you see tangent to the -1, you say inverse tangent or tangent inverse. So you see the sine of the -1, you could read this as sine inverse. You wouldn't want to just spell it by saying sine to the -1. Any questions? I want to take advantage of the fact that we're not just reading this, we're actually hearing it as well. That way, we know what the right words are, or we know how to pronounce them. It's like when we read stuff, sometimes you'll see someone you'll hear someone mispronounce something. And then you'll realize it's because they've only ever read the word. They haven't heard it spoken out loud. There's a mathematician whose name is spelled E-U-L-E-R. And so if all you ever done is read that and your native language is English, you would read that as Euler. But if all you ever did was hear it, you would probably spell it O-I-L-E-R, because it's pronounced Euler. So EU is an oi sound. So use Euler. So if you want to sound like someone who's only ever read math, say Euler. Unless you have some reason to possibly speak German, because then you should read it Euler. Any questions? That's an important one because his name is on everything. He is one of the more prolific mathematicians. This is kind of a product of when he existed, because Euler showed up pretty much right after calculus. Newton and Leibniz are like, oh, look, calculus. And then a bunch of mathematicians, any mathematicians that came after that just got to discover stuff. It's like they opened the door to the treasure room, and then Euler was one of the first guys to run in there. So they go, oh man, look at all this stuff that we're going to discover. I'm going to name all this after me. And then Cauchy is also like, oh yes, me too. Let's name all this stuff after us. So it's like Cauchy and Euler all over the place. And then there's Gauss being like, oh, I've already discovered that Because anytime, because what happened was when you're a mathematician and you found something, you would write to other mathematicians and say, dude, check this out. I don't know if they actually said, dude, check this out. Anyway, the 300 years ago version of dude, check this out. And then they would send it off to mathematician. And then they would write back like, oh, that's pretty cool. I'm gonna steal it. And you're like, oh no, you jerk. And then all of a sudden the book comes out. Like, oh, dang it, Gauss. You know what I mean? So all these derivative statements that we have are now antiderivative statements. These are the ones that I would just expect you to recognize. These are going to be our base models that we're going to start combining with other techniques of integration. But these are the ones that you just have to recognize. So for example, if we want to integrate e to the 5x to x, we know that the integral of e to the 5x, or the derivative of e to the 5x is e to the 5x times 5. So when we integrate, we just divide out the 5. So the integral is going to be 1/5 e to the 5x plus c. The sine cosine thing is the tricky one, depending upon how you decided to remember the derivative of sine is cosine, the derivative of cosine is negative sine. If your way of remembering which one gets the negative is by remembering both at the same time, you'll be all right. If your way of remembering is cosine is the negative one, that's going to mess you up right here. That was a bad way to remember those two derivatives. So the derivative of sine is cosine. The derivative of cosine is negative sine. So when we go the other way, the integral of cosine is sine. The integral of sine is negative cosine. What you can do is check your answer. You're saying that the antiderivative of sine of 2x is negative 1/2 times the cosine of 2x. Take the derivative of negative 1/2 cosine of 2x and see that it comes out to sine of 2x. So the derivative of cosine, negative cosine is positive sine. And then the 2 from the chain rule cancels out the 1/2. Any questions? Is everybody okay? Now, the reason that all these derivatives and integrals were so simple is because all I did to the argument of all I did to the exponents or the argument of our trig function was put in a constant multiple. If we have something other than a constant multiple, then different rules start getting attached. So, for example, if we have the derivative, let's say, of cosine of x cubed, the derivative of cosine of x cubed is negative sine of x cubed times the derivative of x cubed. That's the chain rule. You're always multiplying by the derivative of the inside in the chain rule. So the derivative of cosine of a thing is negative sine of that thing times the derivative of that thing. we can turn this around into an integral statement. But we have to have all of the parts. We have to have all of the features. This x squared is the derivative of the inside. So if I want to turn this derivative statement into an integral statement, I need this x squared there. This -3, that's a constant multiple. I can just divide that out. But this x squared is not a constant multiple. So the integral statement that we get from this is that the integral of -3x squared sine of x cubed dx is cosine of x cubed. The part that we can work around is that -3 factor. If that -3 factor isn't there, I can just take care of it on the other side because it's just a constant factor. So for example, if I modify this a little bit to be the integral of just x squared times the sine of x cubed, the x. The only thing I dropped was the -3. That's a constant factor. I could just divide out the constant factor and have a -1/3 show up on the other side. No problem. If I drop the x squared, all of a sudden we can't do this integral anymore. We don't know how to do this one yet. So if I drop anything that's variable, I don't just get to turn around. This x squared is there from the chain rule. I can't just get rid of that. I can't just divide both sides by an x squared. So if I modified this problem and drop the x squared part out, well, now we're stuck. We don't know that one yet. To make this integration go, I need that just to be the cosine of x cubed. If I want to do that, I need that x squared to be there from the chain rule. Sine of x cubed without the x squared there, we have to do something else. You can't just divide both sides by x squared. If you're wondering, why don't we just divide out the x squared? Then when we take the derivative to get back, we'd have to use the quotient rule. And we will not just get back to sine of x cubed. So for this problem, to just turn it around that easily, to just integrate this as a sine of something, I need that x squared to be the derivative of the inside. To just read this as integral of sine of something is minus cosine of that thing. I need this x squared to be the derivative of the inside. Any questions? How's everybody okay? Yes.
So if that would be basically like x squared tangent x cubed.
Yeah, x squared tangent of x cubed, that'd be fine. The inside is an x cubed, and the x squared is one of the factors of the thing that I'm integrating. Then we're okay. That's the derivative of the inside. We can see that this was just created with the chain rule, and so we can just unchain rule it. The reason that I want to point this out is that differentiation was really nice. Like I said before, there's no function that I can put together that you can't differentiate using the product rule, quotient rule, chain rule. There are integrals that we can put together that you just can't integrate. There aren't nice antiderivatives. There just isn't one. That makes sense? A lot of times people don't like being told that there just isn't a way to do something. But mathematicians can prove whether something exists or something doesn't, or prove that a certain process is impossible, like squaring a circle. You can't, with a compass and a straight edge, trisect an angle. It's just not possible. And it's proven to be impossible. So anybody that says, here's how you trisect an angle with a compass and a straight edge is for sure not trisecting an angle. Barring certain exceptions. If you start with a 180-degree angle, you can trisect that because you just have to build an equilateral triangle, which you can do. And so you'd be like, oh, I just made a 60-degree angle. So that's 1/3 of 180. Then you're like, oh, great. Now you have a 179-degree angle. Trisect that. It's not possible. Anyone says it is possible is incorrect, or worse, lying. You know what I mean? Which is just kind of an uncool move on our part. Because when I'm like selling you something, it's like kind of okay for me to just lie about its properties. Because if you're like, well, this doesn't work, you said it would, I'd just be like, well, no, it should work. There's something wrong with you. You know what I mean? And I go, dude, I'm the victim that got taken advantage of. It's like if you leave your car unlocked and someone takes something from your car, your friends are just jerks. They're like, oh, you should have locked your car. It's like, oh, no, motherfucker shouldn't have taken shit out of my car. You see something that's like on a table, like in the cafeteria or something like that. If it's not yours, here's a thought: don't fucking take it. And if your argument is like, oh, well, they left it there, I guess they don't want it anymore. Or maybe they went to get some coffee and they didn't want to have to pack up all their stuff. But the reason that they have to pack up all their stuff is because jerks like you will come along and say, oh, look, it's a computer. I just take it. You know it's not yours. Leave it there. You know what I mean? But then all of a sudden, well, I guess you shouldn't have left your computer out there. No. The person that took it, no, it's not theirs. They should have just left it. You know what I mean? Humans are a garbage species, and we live in a garbage society. My evidence for this is all the locks that we have to put on stuff. You lock your front door when you left. You know why that is? Because humans are a garbage species that created a garbage society. Just don't go in other people's houses. How about that? Because if you do leave your door unlocked, it's your fault all of a sudden because someone went in your house and stole your stuff. You know what I mean? I guess what I'm saying is, don't be blaming victims. That's not how this works. Incidentally, the answer is not do harsh things to people that steal stuff. That's totally not the answer. The correct answer is to stop building a garbage society where people are motivated to steal stuff, remove the motivation for people to steal stuff, and they won't steal stuff. Because they'll be like, oh, I ain't got to steal that computer because I have one already. I wanted one, and so now I have one. I don't have to steal that car. I've got my own car. You know what I mean? Except for things like supercars. I don't think I think it should be illegal to put locks on supercar doors and require keys to start them. You should just be able to open up any supercar that you find, start it up, and drive it off. That should just be the law. You see an F40 parked in the parking lot, you just get to get in and drive off. That should just be a rule. You know what I'm talking about? That'd be fun. It should be fun for everybody. I've always promised that if I ever win, like stupid amounts of money, I'm going to buy a Ferrari F40 and I'm going to daily drive that. It's just going to be parked out in the parking lot. I'm going to go through the friggin' drive-through. I'm going to deliberately curb the wheels. I'm going to find a car meet somewhere that has like those concrete bumpers. And I'm gonna drive that nose of the Ferrari, that fiberglass expensive ass nose. And I'm gonna slowly just like scrape it right over that thing. $1 million supercar, iconic vehicle from the 80s. And then if there's an opportunity to parallel park at the car meet, I'm gonna be parallel parking slowly. I'm gonna drive in. It's just gonna scrape up those wheels. Then when I open up the door, I'm gonna make sure the door catches on the curb. And I want to see all the Ferrari people just go, oh my goodness, you're ruining the value. And then I'm going to watch all their reactions. I'm going to say, no, guys, I'm getting exactly what I paid for. That look on all your faces. This is a car that was meant to be driven. It's just a tool for getting from point A to point B. Uncomfortably, because it's a Ferrari F40. I don't know if you know much about Ferrari F40s. They're awful as cars. It's like people are like, oh, I want an old muscle car. It's like, oh, no, you don't. If you've been driving a Honda Accord from this century, I promise you, you do not want to drive a 69 Barracuda or anything like that. It will be an awful experience. Cars from the 60s, the 70s are shit. They're terrible at being cars. If you've been driving a modern car, you don't want it. I don't care what it looks like. You don't want it. You know what I mean? I don't know if y'all are into cars, but it's an important thing to recognize. You see that cool 57 Chevy driving down the street? Know that that person, whatever they look like, they are suffering in their soul because they probably have a decent car at home. And like, oh, why am I driving this piece of crap? Because I could have just incognito got into my Honda Civic, driven to the store, got my groceries and driven home, been comfortable the whole time. But instead, I got into this stupid 57 Chevy, which is awful to drive, is trying to kill me. And now I got to stop and have conversations with random people that are like, well, hey, nice car. You want to trade? Because that's what's going to happen. Oh, nice car. You want to trade? Every time you get that fucking gas, you pull up in a Ferrari. Oh, you want to trade? Everybody says that joke like it's never been said before. So if you're ever looking at someone with a nice car and you're like, don't say, hey, you want to trade? You're not being clever. You're just being annoying. You know what I mean? Anyway, what are we talking about? Oh yeah, integrals. Learn your integrals by reviewing your derivatives. That's going to do it for today. I'll see y'all on tomorrow. Everybody have a good day. Thanks for playing.